This is Module 6, Find Angle Measures in Polygons. Our learning objectives for this module, we're going to be finding angle measures within a polygon. The things that you need to know, key vocabulary that you should pay attention to throughout this module is diagonal, interior versus exterior angles, the types of polygons. You need to know up to a dodecagon, which is 12 sides, and the word regular, which we actually talked about a little bit in the previous semester of geometry. So, first things first, what is a diagonal? A diagonal is a segment that joins two non-consecutive vertices within a polygon. So if I have a polygon, for example, let's say I have a rectangle, a diagonal, if I took this point here, that would be one of the vertices. I would just draw a line to a non-consecutive vertice. The other diagonal would be this vertex here connected to the non-adjacent vertex. So that would be an example of drawing a couple diagonals. Interior angles, the original angles of a polygon. So if I had something like this, this is a pentagon. Interior angles would be this angle here, this angle here, this angle here, this angle here, and this angle here. So they're on the inside, so that's why they say interior angles. For exterior angles, again, this was in first semester geometry. For exterior angles, if I had that same polygon, the pentagon, if I extend one of the side lengths and then extend here, that would be an exterior angle here. So same deal here. If I extend in a side length here, that would be an exterior angle. These two angles are going to be congruent because they're vertical angles. And you can do that in each one of the sides. So this would be an exterior, this would be an exterior. This part here is not an exterior. This part here is not an exterior. So that is not an exterior angle. So again, another example, one more example. Angle here and angle here. Those are your exterior angles. So the angles that form linear pairs, that's the key. That's from semester 1. Linear pairs with the interior angles. Okay, so our first theorem that you need to know is the polygon interior angles theorem. And this is an extremely important theorem, and you're going to be using this in one of your assignments in this module. So what the theorem states is that the sum of the measures of the interior angles of a convex n-gon, so that means the number of sides, n is the number of sides, that says that here, is 180 degrees times the number of sides minus 2, or the sides minus 2 times 180 degrees. This is the main thing that you need to remember that you're going to be using throughout this module. So, if I have 6 sides here, in this, I have, I can actually plug this in and say n minus 2, so 6 minus 2, times 180 degrees. If you do that, you get 720 degrees. That means that the interior angles of this polygon will measure up to 720 degrees when you add them together. The corollary to theorem 8.1, which is, remember, corollary, this is again from first semester, it's something that is easily proven using the original theorem. So this is your original theorem. So the corollary is the sum of the measures of the interior angles of a quadrilateral is 360 degrees. Well, most people know about a quadrilateral being 360 degrees because they associate it with a square. So that means if I have this guy here, this guy here, this guy here, and this guy here, you should get 180 degrees when you add them. So for example, x plus y plus x plus y equals not 180, 360 degrees. So add them all up, you get 360 degrees. That's what the corollary states. Okay, so we have our first example, and what I would write at the top of your notes or have it easily accessible is the n minus 2 times 180 degrees. So if we have this, it says find the sum of the measures of the interior angles of a convex octagon. Well, the main thing is you look at these two things. Interior angles means you use this formula. Octagon, you should know, or need to know, has 8 sides. So that means your n, your number of sides, is going to be 8. So all you do is you plug in n, 8, into your formula. So 8 minus 2 times 180. Simplified, you get 6 times 180. And you should get 1080 degrees. That is the sum of the interior angles. So that's 1. What about number 2? So we have the sum of the measures of the interior angles, again, of a convex polygon is 900 degrees. Classify the number of sides that the polygon has. So, which means that we don't know the number of sides, but we do know that the sum of them is 900 degrees. So we could say 900 equals the n minus 2 times 180. Now there's a couple different ways of doing this. Some people like to distribute the 180 degrees to get rid of the parentheses and then solve it algebraically like that. Me personally, I like to divide by 180 degrees. And once you do that, you got 5 here equals n minus 2. Add, and you get 7. It's the number of sides. Now in terms of the name of it, it says classify by the number of sides. 7 is not a polygon, or number of sides is 7, so that means we call it a heptagon. Because hepta means 7. Okay, a few more examples. We have the sum of the measures of the interior angles of a convex polygon is 1440. This is classify the polygon by the number of sides. So this is exactly the same type of question we just had. So again, we have 1440 is what our total angle sum is. We have n minus 2 times 180 degrees. You can do the exact same thing, and when you do that, you get n is equal to 10. So divide by 180 and then add 2. For the fourth example, it says the coin shown is in the shape of a regular 11-gon. So find the sum of the measures of the interior angles. So again, 11-gon, that means that our n is equal to 11. We just plug it into the formula. So we have 11 minus 2 times 180 degrees times 180. So 9 times 180. If you do 9 times 180, you should come up with 1620. Okay, use your calculator for this. Don't try to do it by hand. It just saves you a lot of time. Okay, this is degrees. Okay, so we have the measures of 3 of the interior angles of a quadrilateral. That's kind of key here. Are 89 degrees, 110 degrees, and 46 degrees. Find the measure of the fourth interior angle. So this is using the corollary. Remember, the corollary states that if you have a quadrilateral, they sum up to 360 degrees. So you can say 89 degrees plus 110 degrees plus 46 degrees plus our fourth interior angle, we call it x or y, it doesn't matter, equals 360. Solve this algebraically. You should get x equals 115 degrees. And that's it. Okay, so that's using the corollary. But again, if you don't remember the corollary, quadrilateral, you can always use the n minus 2 times 180 to find out what the interior angle measurements are. Because if you plug in 4, you get minus 2 is 180. Then you get 2 times 180 gives you 360. That's where the 360 comes in. So, again, very important theorem right here. Okay, some more examples. We have find the value of x in the diagram shown. So I look and I see I have 1, 2, 3, 4 sides. I'm just using those to count the number of sides. I'm not using to show congruence. So again, we can use the corollary. So we have x plus 108 plus 121 plus 59 equals 360 degrees. Okay. So when you solve, you should get x equals 72 degrees. And that's it. Okay, number 7 kind of throws some people a little bit because they forget the labeling that's associated with first semester. So remember in first semester, if you have labeling like this or like this, that indicates that the two angles are actually congruent. So it says use the diagram below to find the measure of angle S and the measure of angle T. Well, the first thing we need to know, we're looking at interior angles of 93, 156, 85. We can call it X, and we can call it X because they're congruent. Well, the thing I need to know is what are the sum of the measures of the interior angles of a pentagon, because we have 1, 2, 3, 4, 5 sides. So I know my n is equal to 5. Okay, so if that's the case, I have to use the interior angles theorem, which states that n minus 2 times 180 gives you the interior angles. Well, we know n is equal to 5, so we plug it in. We get 5 minus 2 times 180. When you multiply, you get 540. I'm skipping some steps. Okay, so 540 is what you're going to be using. Just because of space purposes, I'll continue my work up here. That means that 93 plus 156 plus 85. So all I'm doing is I'm taking the 3 interior angles that I know plus x, so I'll say that's 2x. That has to equal 540. So if we know that, we can solve for x and collect like terms. We have 2x plus 334 equals 540. Subtract and divide, you get x is equal to 103. Since they're the same, that means the measure of angle T and the measure of angle S is equal to 103 degrees. And you're done. Okay, so we have theorem 8.2, which is the Polygon exterior angles theorem. So the sum of the measures of the exterior angles of a convex polygon, one at each angle, is always going to be 360 degrees. This is the key thing that you need to know. So exterior angles will always equal 360 degrees. If you don't believe me, what you can do is you can actually draw this figure on a piece of paper, cut out angle 2, cut out angle 3, cut out angle 1, cut out angle 5, and cut out angle 4. If you arrange them to where all of the angles are put nose to nose, point to point, you should have, so you have 1, 2, 3, 4, 5, you should have a circle that is created. And a circle measures 360 degrees. That's why the exterior angle theorem actually holds true. It's always going to be 360 degrees because if you cut out the actual exterior angles, you will create a circle. So, let's get some application with this. So, it asks for the value of x in the diagram shown. So, looking at the labeling in the diagram, we know we have one exterior angle here, one exterior angle here, one exterior angle here, and one exterior angle here. We don't really care how many exterior angles we have, because they always will sum to 360 degrees. So the algebraic method to solve this is, again, you do 2x plus x plus 67 plus 89 will always equal 360 degrees. And again, because they're exterior angles. This does not work for interior. Interior is the n minus 2 times 180. Exterior is always going to be 360 degrees. Okay, so once you do this and you solve, you should get x equaling 68. And it's not 68 degrees, even though it actually follows suit for this one. X is equal to 68 because you have to plug it in, or would have to plug it in to find out the two angle measurements. So it would not be degrees in terms of the notation. All right, so we have a convex hexagon. Has exterior angles again, with measures of 34, 49, 58, 67, 75. What is the measure of an exterior angle at the sixth vertex? So we know 5 of them. 1, 2, 3, 4, 5. That means we need to know the sixth one, which we would say is x. So again, algebraically, we know they're exterior angles, so those are the key words that we look for. So we say exterior angles always measure to 360 degrees. That equals the angles that they're given are 34 plus 49 plus 58 plus 67 plus 75. Okay. Once you do that, you have to add on your x. I'm running out of room, of course. So if you add your x on, because that means you have 1, 2, 3, 4, 5, 6 angles, then you can solve for x, and if you do it correctly, you should get x is equal to 77 when you solve algebraically. Okay, in our last example in this module, it says the trampoline shown is shaped like a regular dodecagon. Remember I told you needed to know up to the dodecagon? That's 12 sides. So it says, find the measures of each interior angle, not the sum of them, each interior angle. That requires another formula that's actually derived from Theorem 8.1. So for A, I'm just going to solve A for now. We know that the interior angles of a always sum to n minus 2 times 180. If we know it's regular, recalling things from last semester, what regular means that you have all the same angles and interior angles and all the same side lengths as well. So these are all congruent if you are actually to go through and label them. They would all be congruent. And the interior angles would be congruent as well. So if you know that, to find the measure of each one, you would have to divide by the number of sides. So this is another theorem, or another formula that's actually derived from Theorem 8.1. So if you want to write this down, that finds the measure of each interior angle. But it only works for a regular polygon. In this case, we're working with a dodecagon, so that means we plug in 12. So we have 12 minus 2 times 180 divided by number of sides, which is 12. So if you did that, you should get the measure of each angle should measure 150 degrees. So that's A. Okay. The measure of each exterior angle. Again, that requires a little bit of thought, but if we know all the exterior angles of a polygon measure to 360, we know again it's a regular dodecagon or a regular polygon. To find the measure of each exterior angle, we would divide again by the number of sides. So we divide by the number of sides in the interior, we divide by the number of sides in the exterior to find each one, but again, it only works for a regular polygon, one that has all the same side lengths and all the same angle measures. So in this case, we know 360 degrees, we know 12 sides, so we divide and we get 30 degrees for each exterior angle. So that's B. So make sure you know this formula and you know this formula that is a derivation of Theorem 8.1 and Theorem 8.2.